So, we have seen a characterization of the continuous linear functionals on LP of mu, where mu was a positive sigma finite measure, 1 was p 1 less than or equal to p, strictly less than infinity. So, we did not look at continuous linear functionals on L infinity. That instead of that, so a substitute result for L infinity result would be to replace L infinity by a class of continuous functions. So, we have seen this before. We saw Riesz representation theorem. This was for positive linear functionals defined on continuous functions on compact support, right. So, Cc of x, where x was a locally compact Hausdorff space and Ccx was continuous functions with compact support. So, we will be looking at a slightly bigger space Ccx if you put the supremum norm. So, that is the L infinity norm in fact, that actually will complete to a space called C0 of x, which I had defined some time back. This is the class of continuous functions vanishing at infinity, and we will look at. So, then this space becomes a normed space with the supremum norm, and it is complete with respect to the corresponding metric. So, it is like the LP spaces, except that, so you can think of C0 as a substitute for L infinity, and they are not same, and we will be looking at continuous linear functionals on C0 of x, and we will prove the full version of Riesz representation theorem. So, that is our aim. Okay, so let us start. So, our setup is that we have a locally compact Hausdorff space, okay, and the function space we are looking at. So, generally we have a measure and we look at LP. Now, we look at the function space C0 of x. The 0 says that it is vanishing at infinity. So, how does one define this? So, you look at all those functions which are continuous, complex valued functions, continuous, such that for every epsilon positive there exists a k epsilon which is compact. The compact set will depend on epsilon, such that if x is not in k epsilon, then mod f of x is less than epsilon. Okay. So, what does that mean? So, I have some space x, this is my locally compact Hausdorff space. So, for a fixed epsilon I should get a compact set. So, compact set would be something which is inside x. Outside that the function value here is less than epsilon. So, it is much smaller as you go towards infinity, that means away from compact sets, then the function would be smaller and smaller. So, let us look at the real line as a typical example of a locally compact Hausdorff space. C0x are continuous functions which are becoming smaller and smaller outside compact set, which means that they should go to 0 at infinity. That is why this space is called vanishing at infinity. So, if you recall, I had given some exercises. You can compactify x by adding a point at infinity. So, that is x tilde as x union infinity. This is called the one point compactification. And C0 of x is precisely all those functions in C of x tilde. So, x tilde is a compact T2 space. So, I am looking at all continuous functions on that, such that f at infinity is 0. Okay. So, that is one way of seeing the space. If you are not familiar with one point compactification, you can ignore this and you can stick to the real line or Rn. Okay. So, all that I am saying will be true for Rn, because Rn is a locally compact Hausdorff space. Now, suppose mu is a Borel complex measure on X. Okay, what does that mean? So, we have X with the topology. So, we have the Borel sigma algebra, right? Borel sigma algebra of X, Borel sigma algebra of X, right, generated by open sets. Mu is a complex measure defined on B of X. So, first I want to define the integrals. Okay. So, if I take f in C0 of x, I want to define integral of f with respect to mu. See, we do not know this yet, right, because mu is a complex measure. If mu is a positive measure, we know how to define this, but if mu is a complex measure, well, what do? We use the Radon-Nikodym theorem, which we have seen earlier. So, d mu can be written as h times d mod mu. What is h? H is such that mod h equal to 1, right. So, h is a function whose modulus is 1. So, I can use that to define the integral of f with respect to mu. So, that is f times h d mod mu. Now, this makes sense because mod mu is a positive measure, right. So, mod mu is a positive finite measure. So, I know how to integrate any reasonable function against it. So, f times h is measurable, it is bounded because f is in Z0 of x. So, the L infinity norm of f with respect to well, L infinity norm here means simply supremum over x in x mod f of x. This is finite because it is less than epsilon outside a compact set, and on a compact set it is bounded, right. So, that is why. So, f times h is a bounded measurable function and mod mu is finite. So, this integral makes perfect sense. Okay, it is finite, and moreover, if I look at integral over x f d mu, which is by definition f h d mod mu. So, now I can take the modulus inside and get a bigger quantity because I am integrating against a positive measure. So, this is less than equal to integral over x f times h modulus d mod mu, but mod h is 1. So, this is integral over x mod f d mod mu, right. So, that is quite nice because here I have integration against complex measures. So, when I take modulus, it is not just f, I have to take the modulus with mu also you should keep in mind. Okay. Well, so what is the advantage of this? This I can write as it's less than or equal to, I take the supremum of f outside. So, that is the norm we have, times what remains is the total mass of x, right, okay, and which is finite. I know that this is finite. So, this tells me that if I define, so define T of f, okay, to be integral over x f d mu, where f belongs to C0 of x and mu is a complex measure. In that case, mod T of f is less than or equal to, so that is the integral which we just computed to be bounded by the supremum norm of f times mod mu of x, right. So, this is a constant mod mu of x. So, whenever we have such a condition, we have continuity, right. So, this immediately implies that T is continuous. Okay, such a, well, it is an integral. So, T is linear. So, T is linear. Maybe I'll write it down this just after continuity part. Okay. So, T is continuous. Why is T continuous? Well, if Fn converges to f in my space is 0 C0 of x. So, it has to converge in that norm, right. So, that is same as saying Fn converges to f in the supremum norm, which is uniformly, right. So, this goes to 0. So, I can plug this in here. So, I will get modulus of T Fn minus T f, right. I want to know whether this goes to 0. This is because t is linear, fn minus f less than or equal to some constant, that is mod mu of x, times the L infinity norm or the supremum norm of fn minus f, which goes to 0. So, t is continuous. Okay. So, you have seen this, whenever you have inequalities like this, you will get continuity. Okay. So, why is t linear? So, because we have some definition. So, you have to use that. Okay. So, t of f plus g, for example, is defined to be integral over x f plus g d mu, but integration against mu, mu is a complex measure. So, this is integral over x f plus g h times d mod mu, but the integration with respect to positive measure, you know that is linear. So, that is integral over x f h d mod mu plus integral over x g h d mod mu, right, which is tf plus tg, right. So, that is why t is linear. Okay. So, remember that this is actually a symbol, it is defined to be this particular value. Okay. All right. So, we continue. So, what did we do? If I take a Borel measure on x, we get a continuous linear functional. Okay. Our aim is to prove the converse. Okay. So, aim is to prove the converse of this. That means, if I have a linear functional, it is given by a measure. Okay. So, for that, let us let script m of x be the collection of regular Borel measures, regular Borel complex measures. What does that mean? So, I did not tell you what regular is. Borel complex measure you already know, a complex measure defined on the Borel sigma algebra. Regular here means that, so mu is regular, mu is a complex measure, right. So, regularity has to be defined. Mu is regular means, so if and only if mod mu, so mod mu is a positive measure, and you know what that means to say mod mu is regular. So, right, appropriate inner regularity and outer regularity are true for mod mu, that is enough. Okay. So, now we are in a position to state Riesz representation theorem. So, Riesz representation theorem for C0 of x. Okay. So, now we do not assume any positive linear functionals or anything, we will start with a continuous linear functional, right. So, I have x locally compact T2, then every continuous linear functional on C0 of x is given by a complex regular Borel measure. Okay. What does that mean? That is, so let us write it in mathematical symbols. That is, if I have a continuous linear functional phi from C0 of x to the complex plane. So, remember C0 of x is a complex vector space, and with respect to the supremum norm, it's a complete metric space. Okay. So, it's like LP we have seen earlier, we had a norm there which is with respect to which LP is complete, and it was a complex vector space. Similarly, we have C0 of x. So, if I have a continuous linear functional on C0 of x, then there exists unique mu in Mx, right. Mx, remember, is the class of regular Borel measures on x. So, there is a unique mu such that phi of f is defined to be integral x f d mu, right. So, that is how the linear function is given. So, recall that integral over x f d mu was defined to be integral over x f h times d mod mu. Okay. So, we know to define this only in this form. Of course, you can start with another definition, you will see that they are all same. Okay. So, I will comment upon it after I finish the Riesz representation statement of the Riesz representation theorem. So, phi f is this. So, this is the important part of it, but remember we had some norm equality in the case of LP, right. Norm of the linear functional was the LQ norm of the function. So, that continues to hold here. So, we have, and well, how do we define the norm of phi? So, norm of the linear functional, remember, is defined to be the supremum over the unit ball, right, of the space. So, the space here is C0 of x. So, you look at all C0 x functions whose supremum norm is less than or equal to 1. So, that is the unit ball, and take the supremum of mod phi f, where f comes from the unit ball, right. So, this is actually mod mu of x. Okay. So, that is like complete identification of the dual of or the continuous space of continuous linear functionals of C0 x. Okay. So, let us, before we go to the proof, let us just comment on the integral part. So, integration is defined like this: mu is a complex measure, right. So, I can write mu as, well, mu 1 plus I mu 2, mu 1 plus I mu 2, right, because it has positive and real and imaginary part. So, where mu 1 and mu 2 are signed meshes, right, real meshes, signed meshes. Okay. So, then we can use the decomposition. So, hand decomposition or Jordan decomposition or whatever we called it. Mu 1 I can write as mu 1 plus minus mu 1 minus, right, plus I times mu 2 plus minus mu 2 minus. Okay. So, if I define this, there is a natural way of defining integral of x f d mu, because now all these are positive meshes, correct, and then you know what to do. You can define it to be integral over x f d mu 1 plus, right, minus integral over x f d mu 1 minus plus I times the same quantities here, right. So, you can do that as well, because these are all now positive measures, and so these integrals are well defined. You will get exactly the same by this definition, right, because h. So, let me write down that h d mod mu, right, this is my d mu. So, if I write mu as mu 1 plus I mu 2, okay, I can write h as h1 plus I h2. Okay. So, this will be h1 d mod mu plus I times h2 d mod mu. So, these are the Radon-Nikodym derivatives for mu 1 and mu 2, right, and then h1 will take plus or minus 1 values, and h2 will take plus or minus 2 values, and so on, right. So, you can, anyway, you can, this is something I will leave it to you. So, and just to check that they give you same kind of results. You will have to modify a little bit, but it's essentially easy argument to say that it gives you the same integrals. Okay. Okay. So, Riesz representation theorem is what we are trying to prove. Okay. Now, the proof is slightly long. So, what do we do is we use the positive linear functional. So, first we will find a positive linear functional lambda on Cc of x such that mod phi of f is less than or equal to lambda mod f. for every f in CCX. Okay, so that is our aim. Well, why are we doing this? Well, first we want to use the this representation theorem which we had written down earlier, right? We wrote down RRT on CC of x, right, for positive linear functionals, okay. So our aim is to if I have a linear functional phi on C0 of x, of course it defines a linear function on CCX as well. So phi is supposed to correspond to some measure mu, okay, and the lambda we will find will correspond to mod mu, okay. So because mod mu is a positive measure, right, so that will define a positive linear function, and then from this we will construct mu using phi. So that is what we will do. So first we define lambda, that use the Riesz representation theorem for positive linear functionals, which will give us a positive measure, and from that we will construct the complex measure. So the definition is like this. So if f belongs to CC of x plus, okay, what is CC of x plus? All positive functions in CCX, okay. So look at all continuous functions with compact support, and you look at the ones which are positive, okay. So that is CC plus, okay. For on that define lambda of f. So lambda, remember, is going to be a positive linear functional on all of CCX. Right now I am looking at only the ones which are positive, right. So lambda of f to be, well, this is sort of very natural definition if you think about it, supremum over mod phi of g, okay, where g belongs to CC of x, but mod g is less than or equal to f. Remember, f is positive or non-negative, so mod g less than to f makes sense. I am looking at all those g such that mod g is less than or equal to f. So if it is given by integrals etc., you take the modulus and you take the supremum, you will see that this is exactly what we want, okay. I mean, assuming that the theorem is true, phi of g would be integral over x g d mu, right. So you take modulus and all that, this goes away and you will have mod mu, and you take the supremum over g such that this happens, you will get integral f d mod mu, right. That is precisely what we want as lambda, okay. So that is why this is defined. Of course, we need to prove a lot of things with this lambda, okay. But some of the things are very easy. So then if I define like this, then, well, first of all lambda f is positive, okay, and if 0 less than or equal to f1 less than or equal to f2, well, what can you say about that? You will be looking at all those g and then taking mod g less than or equal to f and then take the supremum. So right, that is a collection you will be looking at. So for f1 the collection will be smaller than f2 because f1 is less than or equal to f2, and so when you take supremum, of course things will be bigger, right. So this would immediately imply that lambda of f1 is less than or equal to lambda of f2, okay. So well, you can put brackets if you want, but it should be clear what I mean by, okay. So that is one property, and an easy property is lambda times CF, lambda of CF is equal to C times lambda f for C positive, okay, and f is of course in CCX, CC plus x, right, because if I multiply f with C, that is like multiplying g with C, and that C comes out from phi because phi is linear, and you have a modulus phi coming out, modulus C coming out, but C is positive. So this is C comes out, okay. So that is these are all trivial assertions, so just follows directly from the definition, okay. So now to show that, remember we still haven't defined the linear functional, okay. It is defined only on non-negative or positive continuous functions with compact support CCX plus, right. So we show that it is linear there. So lambda of f1 plus f2 is lambda of f1 plus lambda of f2, okay. For f1 f2, in CC plus. So, on CC plus it is additive. Okay. Okay, so how do we do this? So, this is an interesting proof. For every epsilon positive, there exists H1 and H2 in CCX, okay, such that lambda F1 is less than or equal to modulus of phi of H1 plus epsilon, lambda F2 is less than or equal to modulus of phi of H2 plus epsilon, right. So, this is just the property of the supremum, right, because lambda is the supremum of certain things. So, if I look at lambda f minus epsilon, there would be some element here, right, that we have seen it several times, we have used it several times for outer measure and so on. So, that is precisely what is happening here. Okay. Now, in this, well, so there exist complex numbers alpha 1, okay, alpha 2 in C such that mod alpha 1 equal to mod alpha 2 equal to 1. So, modulus is 1 and modulus of phi of H1 is equal to alpha 1 times phi of H1, and similarly modulus of phi of H2 is equal to alpha 2 phi of H2, right. You multiply by an appropriate e to the I theta, you will get the modulus. Okay. So, if I look at these two things and add, okay, so add, we will get lambda f1 plus lambda f2, this is less than or equal to mod phi of h1 plus mod phi of h2 plus 2 epsilon, let us say, right, epsilon plus epsilon, 2 epsilon, does not really matter, epsilon will become as small as possible soon. Now, I replace phi h1 and mod phi h1 and mod phi h2 by whatever is on the right hand side. So, this is equal to alpha 1 phi h1 plus alpha 2 phi h2 plus 2 epsilon, right. But phi is linear, right, phi is a linear continuous linear functional on C0 of x, right. So, in particular on CCX, and alpha 1 and alpha 2 are scalars. So, I can write this as using linearity, this is alpha 1 h1 plus alpha 2 h2 plus 2 epsilon, right. Okay. So, these are all positive anyway. So, I can write this as less than or equal to, use the definition of lambda, I will get lambda of the modulus of this function. So, one thing you should always remember is that if I look at mod phi g, that is less than or equal to lambda of mod g, right, because g is one such g is one element in the set where you are taking supremum. So, use the definition. Okay. So, this I can take modulus of whatever is inside here, but alpha 1 and alpha 2 has modulus 1 and I have monotonicity for lambda. So, I will get mod h1 plus mod h2 here, okay, plus 2 epsilon. Okay. So, I missed one crucial ingredient here. So, let me, okay, here the condition is that h1 is less than or equal to f1, right, that is the set where you take supremum, mod h2 is less than or equal to f2, right. So, you choose h1 and h2 so that these inequalities are true, and then we start from lambda f1 plus lambda f2, we have got this as on the right hand side. But h1 and h2, mod h1 and mod h2 are less than or equal to f1 and f2. So, I can replace this by lambda of f1 plus f2 plus 2 epsilon, right. So, I have this equal less than or equal to this plus 2 epsilon for every epsilon, right. So, let epsilon go to 0, this implies lambda of f1 plus lambda of f2 is less than or equal to lambda of f1 plus f2. So, it is not linearity, it is an inequality which we have got. If we prove the other way inequality, we are done. Okay. So, to prove So, to prove that lambda of f1 plus f2 is actually less than or equal to lambda of f1 plus lambda of f2. Okay. Okay. So, for this choose G in CCX, okay, such that mod G is less than or equal to f1 plus f2, right, and then you take supremum over such things to get lambda of f1 plus f2. Okay. So, this requires some construction. So, let V equal to the x such that f1x plus f2x is greater than 0. Okay. So, since it is greater than 0, this is an open set, okay, open set in capital X, right, because f1 plus f2 is continuous. So, define. So, now we are going to split f1 plus f2 into two parts, right. So, define g1x to be equal to f1x divided by f1x plus f2x times g of x. Okay. So, we took g such that this is true. Now, I will split g into two parts, so that one part is less than f1, the other part is less than f2, right. So, that is what we are doing, and g2x is f2x by f1 plus f2, f1x plus f2x times gx of course. Okay. So, this is for x in V. V is the place where we have strict positivity. So, I can divide, right, otherwise 0. So, g1x will be 0 for x not in V, and g2x will be 0 for x not in V. Okay. So, if you look at it carefully, you will see that because you are multiplying by g and because of this inequality and you are dividing by f1 plus f2, these are all continuous functions. So, there is no 0 by 0 coming anywhere, and there is no problem with well definedness. Okay. So, check that. So, this is pretty easy. Then check that g1 and g2 are continuous functions with compact support, okay, and g1 plus g2 equal to g, mod g1 is less than or equal to f1, mod g2 less than or equal to f2. This is what we wanted. Okay. We had a g which is bounded by f1 plus f2. We are splitting g into two parts where these two are true, right, because that is the set where which you take supremum. Okay. So, we will stop here. So, we have just started with the proof of Riesz representation theorem. I told you it is slightly long. The method of the proof is to construct a positive linear functional which dominates the given continuous linear functional phi on C0. Okay. So, we have constructed this lambda which is bigger than phi in some sense, and we have proved that lambda has certain properties. So, we need to prove lambda is linear. We proved one way inequality, that lambda of f1 plus lambda of f2 is less than to lambda of f1 plus f2. We will prove the other way inequality to prove that lambda is linear at least on Cc plus x, continuous functions with compact support which are non-negative, and then we can extend it linearly to the whole space. So, that is the idea. Okay.